Hello, everyone. My name is William Glavin. My project is called Detecting and Reclassifying Pitch Type Evolutions using Statcast data. Um, so I've always been a huge baseball fan, and we are living in the golden era of baseball statistics. And there's so much interesting stuff going on right now. I guess, to be honest, the main thing that facilitates the ease of doing a project like this is the use of a Statcast API, Pi Baseball, to retrieve data and pick and choose data however you like to show. I wanted to explore how we can use machine learning, specifically clustering and PCA, to understand how pitchers' repertoires change over time. So pitchers throw a bunch of different kinds of pitches. Young pitchers are figuring it out, changing their pitch shapes and types along the way. Pitchers come back from injury and sometimes are restricted because of movement to throw their pitches a certain way. Pitches can behave differently over time. I've always been interested in baseball analytics, and this was a great way to apply the algorithms we learned in class to a real data set and a real world question. And so, for the practical problem and background, like I said, in baseball, each pitch a pitcher throws, like fastball, slider, curveball, is tracked by Statcast, which measures velocity, spin, and movement. The problem is that these pitch classifications often lag behind what pitchers are actually doing. And when a pitcher tweaks their grip, release, or spin, it might technically become a new pitch, but public data sources like the Baseball Savant might not recognize it right away. Baseball Savant is another great resource. My goal in the project is to see if I could use unsupervised learning like we've learned in class, so clustering and dimensionality reduction to detect when those changes happen automatically. And so this is an example of a pitcher who's pretty young, 23 years old, Cam Schlittler, who's a rookie this year. Interesting thing about guys like him is that the pitches can change as he's learning pitches, so the data is changing. And this is a visualization that shows what different pitch types look like in movement space. And so each dot represents average horizontal and vertical movement. You can see the pitches moving for a specific pitch type from Camp Schlittler's Statcast data. And so this is kind of like a fingerprint for each pitch. The fastball moves differently from the changeup. You see the fastball there not moving much at all, the red. And the slider is its own cluster. In Cam's example, he's throwing a lot of cutters up here. He's got a curveball. He's still learning new pitches, so this data is changing, which makes it really cool. Um, this visualization helps us understand the kind of separation we expect when we apply clustering later. This is like a physical map of how pitch types differ in shape and spin. So for the machine learning problem, how does this become a machine learning problem? I approached it as an unsupervised learning task because I didn't try to predict a label. We let the data group itself. I used k-means and db scan to cluster pitches based on features like velocity, spin rate, and movement, data we have available. And then we use PCA, principal component analysis, to reduce those features down to two dimensions for visualization. The idea is that we can see natural clusters forming or especially changing over time. It might correspond to the pitcher developing a new pitch or altering an existing one. So this is an example of a different pitcher, Mike Soroka, another like opposite end of the spectrum, maybe like later in his career, uh, he can't throw as hard, so the pitches move differently. He has to rely more on movement than pure speed and velocity. So this is what the PCA projection looks like for just his data. You see the pitch types there. Each point here represents an individual pitch thrown. Each color is a cluster identified by the algorithm. You can see clear separations between some groups, which are pitch types, and smaller overlaps when the features are similar. Like a sinker and a two-seam fastball, for example, behave very similarly. We also check the silhouette score to make sure clusters weren't arbitrary. Positive score means we have reasonably distinct groups. This kind of visualization helps validate that the features we choose, velocity, spin, and break, carry enough information to distinguish between pitch types. And so this is a Garrett Cole's 2023 pitches evolving over time. So we're looking at how the features evolve throughout the season. We start to see the motivation for this project. This shows his velocity and movement across 2023. You can see that both velocity and movement vary month to month. And so those small but consistent changes could signal grip adjustments or fatigue, especially in this case, which is interesting because obviously about a year after this, his elbow gave out, which is sometimes corresponds a lot to like a spike in or a decrease in velocity. Like you can see the velocity trailing off here a little bit. Um, so this kind of variation is what clustering algorithms can help quantify and visualize automatically. So yeah, this is kind of interesting because he is on the mend now, just had elbow surgery 2 years after this. And so for the data description, all the data comes from Baseball Savant's Statcast system, which tracks every pitch in Major League Baseball. We use the Python library PyBaseball to pull data for individual pitchers, about 3 to 4,000 pitches per season. Obviously varies. Cam Schlittler only pitched for 2 months when he came up. The main features include velocity, spin rate, spin axis, and both horizontal and vertical break, along with the release position. And interestingly enough, like Cam Schlittler is 6'4", so his release point is super high, which actually makes it difficult for the hitter to discern between pitches if they're all coming from like that high of a release point. I normalized all numeric features using z-scores and filtered out extreme outliers, which helps the clustering algorithms treat each variable on an equal scale. Um, So there you can see this is more data pulled from Statcast. This is like a sample of Mike Soroka, some random start in July of this past year when he was pitching for the Nationals. This is like a sample of the data you can pull from the API. You can select different and output as CSV. And this is another young pitcher who we'll get into in a second on the Nationals. And another interesting case, another young guy, 22 years old, coming off major elbow surgery, which restricts, what he's able to do. But so this is a game they pitched about a month after he came up in early September against he's throwing a knuckle curve there. You see the release speed, release position, and this is like a unique identifier for him. The outcome, we don't need that in this case. And like I said, just lots of cool data you can pull based on, and this is again Cade Cavalli just showing more data you can pull. So this is Cade Cavalli's release point. Again, he's a taller guy, like 6'5". This is showing it evolving over the season. And so, obviously, like his first start coming up, and so things are going to change. He's going to find out what works, what doesn't work, and he's going to change it over time. And so, yeah, each of these is a pitch. And so you can see small but measurable changes over time, and that's what we're looking for. For the planned experiments for this project, here's how I structured the project. Explore the data to understand the distributions and relationships between features. Then normalize the data and remove, pardon me, outliers, and then apply two unsupervised machine learning algorithms, k-means and dbScan, and use PCA to visualize the results. And evaluate the clusters both visually and numerically with the silhouette score, and compare them to the official StatCast pitch labels to see how well they align. And so my prediction is, and this is so cool because there's so much information about how these are just constantly evolving right now. If we cluster pitches based on their physical characteristics, they could correspond to pitch types. And if mechanics or pitch shape changes mid-season, that could show up as a new cluster or a shift in existing ones. So just by looking at the data, might detect a new pitch or a pitch, evolves before it's recognized publicly. So a lot of people are able to do now. And so potential outcomes. The goal isn't to build a production level model, but to demonstrate that unsupervised learning can uncover real structure in this data. I expect to produce visual evidence of pitch clusters shifting over time, possibly detect pitch changes earlier than official databases. That would be really cool. This type of analysis could be expanded later into scouting or player development tool. There's a lot of information out there, but here it mainly shows what we learned in class. And references, obviously, we're using that Baseball Savant. incredible website using their API. Fangraph's another great resource for pitch classification. I plan to test this process on additional pitchers and tweak clustering parameters to see how stable the results are. And yeah, I appreciate you guys taking the time to listen. Thank you so much.